So I'll be talking to you guys about human-assisted cyber reasoning systems, which combines two topics that I'm passionate about, cyber reasoning systems and the human race. So this work was done in collaboration with a number of really great people, most of whom are at this conference. So if you see them, say hi. I'll point out two of them are on the market. Michael Weisbacher, he's on the market this year, and Fish Wang is on the market. So if you see those come across your desks and search committees, pay attention. You can follow along with this talk at that link down there. And without further ado, we'll launch into the history of cyber reasoning systems. First from, hold on, don't panic. All right. First, from the perspective of humans. Throughout the history of our field and throughout the history of our species, we have had humans telling humans what to do and essentially dispatching humans to perform tasks. If you read one of the very early papers on this concept of what if we actually try to formally find bugs in software, written by Alan Turing in 1949, it's very interesting. You read this paper, and he's describing, methods that you would take to ensure that the program is bug-free. And he's talking about this bug-checking system, but the language is a bit strange. And at one point, a couple pages in, he uses a human pronoun for the system. And then you have this realization that Alan Turing didn't think of cyber reasoning systems that find bugs in software. He was thinking about humans finding bugs in other human software in a formal way. So that is kind of the, traditional way, even in our field of cybersecurity, how we think about dispatching of tasks. And, fast forwarding a little bit, of course, we start to use automated approaches, or we start to use tooling to help humans. So the stage fright bug that wreaked havoc on Android phones a little while ago was found through repeated iterations by a human of an autonomous fuzzer, or a, fuzzing tool, specifically AFL. And the human would run the tool, look at the results, run the tool, look at the results, and so on. And as time goes on, we try to replace more and more humans on the bottom of this hierarchy with automated techniques. Until last year, where there was this interesting concept of cyber autonomy that was given quite a few $1 million and explored in the context of a competition, the DARPA Cyber Grand Challenge. The Cyber Grand Challenge pitted 7 fully autonomous cyber reasoning systems with no humans involved against each other in a cybersecurity competition where they had to analyze never-before-seen software, find bugs, exploit those bugs, and fix the bugs. And of course, our team Shellfish participated in the Cyber Grand Challenge. That is our cyber reasoning system right there on stage in Las Vegas. And this is where this research really stems from. The Cyber Grand Challenge, again, was fully autonomous under pain of violence. There were Army personnel guarding the air gap that separated these systems from their human creators. This autonomy pervaded, of course, every part of the design, and it had several implications specifically for bug hunting. Every detection of a bug by these systems had to be directly actionable. There was no human to whom you could report a bug and have them triage it. There was no, false positive metric that you could wave away in a paper. It really had to find and be able to trigger real bugs. So this mandated the use of dynamic techniques for the bug hunting component of these cyber reasoning systems. And in turn, it means that the biggest problem facing cyber reasoning systems in terms of bug finding is the dynamic coverage problem. This is a problem we're all familiar with. Given a control flow graph of an application, if there's a bug somewhere over deep down inside, with the top left corner being the entry point and that red dot being the bug, you can't identify that bug dynamically without actually triggering that code, being able to run it. And so cyber reasoning systems have developed, or humans have developed for cyber reasoning systems, this paradigm of trying to cover a lot of code very quickly with very scalable but not very complex techniques. And then when that fails, trying to move up the chain of semantic reasoning capability to run increasingly less scalable tools to try to increase dynamic coverage. So I'll show you kind of what this means in the context of the Cyber Grand Challenge. And this is the paradigm used by every single cyber reasoning system in the Cyber Grand Challenge, every single one. First, these systems start out with a fuzzer, a simple fuzzer, and specifically each cyber reasoning system in the Cyber Grand Challenge used American Fuzzy Lop. And this fuzzer, run against our sample application, might achieve some small amount of code coverage. And it is quite effective on its own, not to underplay the effectiveness of fuzzers, but it runs into issues that prevent it from achieving more dynamic code coverage. These issues are wide and varied. A couple of very simple examples are magic numbers, complex hard-coded strings, or maybe not so hard-coded strings, harder to analyze those, and dependencies between data. Like the standard highly scalable, low semantic complexity fuzzer such as AFL doesn't reason about dependencies between data inputs. And so in these cases, it's unable to satisfy these checks and trigger that code inside the brackets that's in red. And so when this happens, we have heuristics that say, okay, the fuzzer is stuck, and we move up this chain of semantic reasoning, and we launch into a technique that is more complex and less scalable. So for example, symbolic execution. That is the icon of Anger, our symbolic execution engine, and our binary analysis framework does more than just symbolic execution that we use for the Cyber Grand Challenge, but any symbolic execution engine can plug in here, and in fact, there were many at the Cyber Grand Challenge. And symbolic execution pushes the coverage a little farther in the context of these cyber reasoning systems, but it has very well-explored problems, path explosion, the complexity of SMT solving, and so on. And so it also gets stuck. And you can get a little farther by having crosstalk between these. So you have symbolic execution, synchronize test cases back to the fuzzer, and you achieve more coverage on the program. But you're still missing some in very many cases. And so, and the reason that you're missing this code coverage to get to the bug in this case is a little more complex than the drawbacks of fuzzing. It's really this sort of very complex state-dependent checks. So some of these applications require you to input perfectly presented expressions, right, to interact with them. Some applications require you to get an application into a very specific state, analogous to a victory state of a game before a bug can be triggered. You might just have an application that tries to give you a Turing test. I don't know how that might work, but it's hard to list these examples on a slide. But the bottom line is there's something about state that we don't quite have even the terminology to discuss as a community that keeps these cyber reasoning systems from achieving the dynamic code coverage that we would like them to achieve. And normally in this paradigm, we would just move up, have a magic analysis that achieves reasoning about this state at the cost of even more scalability. But we don't have anything like that. And so we ran into this problem, of course, in the Cyber Grand Challenge, where we saw that the mechanical fish was, our cyber reasoning system was suffering to achieve code coverage in these more complex applications. And we stumbled onto a solution. at DEF CON CTF, right after the Cyber Grand Challenge, where humans faced off against the cyber reasoning systems in the CGC environment. And we did, and so we were very tired from preparing for the Cyber Grand Challenge. We were not functioning at the 100% that DEF CON level hackers typically function at. And so we kind of acted as helpers for our cyber reasoning system at DEF CON CTF. We noticed that there were problems that the CRS was having achieving specific dynamic code coverage, and we took it upon ourselves to be the higher semantic reasoning analysis that is missing from the chain. So what we did was essentially interact with the programs that the cyber reasoning system was trying to analyze at DEF CON and allow it to observe our interactions. And then we went out to dinner. And when we came back, the cyber reasoning system had found a vulnerability by synchronizing the test cases that we produced, automatically exploited the vulnerability, automatically patched it, and deployed the patch and the exploit against the other teams at DEF CON CTF. And so this was very cool to see. And it really, in that case, it solved this dynamic coverage problem, right? There was something that the CRS couldn't trigger. Human assistance helped it trigger it. And we essentially stumbled upon a new paradigm. I'll draw your attention to the fact that we went out to dinner after interacting with these programs a bit. The system was autonomously running while we were eating. And so we have a paradigm here where there are autonomous systems that can use autonomous techniques, and when they need help, they can turn to humans for assistance, much in the way that you might turn to a friend for assistance, but you're still an autonomous human being. These are human-assisted cyber reasoning systems, hackers. And one thing we realized, the reason I stressed how exhausted we were and how we weren't hacking at our best, is that we weren't really acting like master hackers here. We were acting like users of computer software, not cybersecurity professionals. And so we realized that you could really have normal people, non-experts, interact with this software and help cyber reasoning systems. And we took it a step further. What if you could create a CRS that, using a scalable API, was able to ask for help from humans around the world, from a very scalable, maybe not as scalable as automated techniques, but still as scalable as human effort goes, supply of human labor. So we combined the Amazon Mechanical Turk with the Shellfish Mechanical Fish to create the HaCRS, the first human-assisted cyber reasoning system. In order for this to work, of course, we need an interface that allows non-expert humans to interact with the cyber reasoning system. This interface we created to be a web UI launched over Mechanical Turk, and really embracing the goal of what we want from the humans, and that is interactions with the program. So the core of the system is this terminal, web VNC terminal, essentially, where the humans can interact with an application that the cyber reasoning system is analyzing. Of course, the initial design of this left humans fairly confused. You get a black box, and you know, what do you do with it? Well, we helped them out by providing them with example interactions. Test cases synchronized from the automation and from other humans and from a combination thereof to give the humans an idea of how to interact with this software. And we can go one step farther. Earlier, I mentioned that dynamic analysis is king in cyber reasoning systems. But by having a human in the loop, we can now utilize static analysis to some extent. So we perform static analyses on programs as they're executing these example test cases to give humans overlays that provide helpful alternatives and other information that for a cyber reasoning system is not directly actionable, but for a human can influence their thought processes and allow them to assist the cyber reasoning system better. And we gamified this whole thing. because humans love games. So we gave a goal for every human for how many control flow transitions we wanted them to trigger in a program. Once they reached that goal, we had bonus goals for them that would give them bonus payouts through Amazon Mechanical Turk. And this isn't big money. Mechanical Turk workers don't earn six figures incomes, unfortunately. But we found that just the idea that there is a next step, a goal, a bonus, really motivated these people to work very hard to help our cyber reasoning system. We ran these experiments. We ran experiments to assess the usefulness of this approach. We took 85 programs that are human interactable from the Cyber Grand Challenge. And so this is actually a relatively important filter. This human-assisted cyber reasoning systems in their current state can only really help with human interactable programs. It's not a giant limitation. Many, many programs are really made for humans to interact with. And so we picked 85, which is also the size of the data set in the final event of the Cyber Grand Challenge. We recruited 183 non-experts from Amazon Mechanical Turk. This was fairly easy. The most complicated part of getting scaling out to 183 people is dealing with the API of the system, which luckily I didn't have to touch. That was all Michael. We also recruited 5 semi-expert humans. And these are undergrads, master students in computer science, and these are much harder to come by, right? We were very easily able to scale to 183 non-experts on Mechanical Turk, but we were only able to get 5 semi-expert volunteers. That's a bit unfortunate because we weren't able to explore the impact of expertise as much as we had wanted, leaving the door open for some follow-on work in that direction. This all cost us a total of $1,100, which was also a very hard figure to compute because Mechanical Turk has a bit of an obscure API in terms of understanding how much money you actually spend, which is not a lot. The prize money in the Cyber Grand Challenge was in the order of millions. 1,100 is something I would have personally paid to get the increase in results that we got. And we ran a number of experiments, both with and without human assistance, for 8 hours each. Before running the experiments, we sorted the data set into programs that we felt were semantically complex, which is to say, are there those complex transitions that require a lot of reasoning about state? The example that I always give is one of the programs in this data set is a pizza ordering system, an online pizza ordering system. And for that, you have to reason about pizza, which is not a concept that really exists in autonomous analysis systems. You have to understand that first you have to select the crust, then you have to select the cheese, then you have, and so on, versus a file format, which is not an image parser, for example, which is not semantically complex, which has data that has very specific meaning, approachable by an automation. And we rank these systems into the relative complexity of computer science terms or computer science concepts that are involved. So an example of a high expertise system is a programming language interpreter that humans actually need to provide well-formed inputs into to explore. We ran 3 experiments. Well, we ran more. I'll present 3. Just pure fuzzing, not assisted by symbolic execution or by or by humans. Driller, our prior work of symbolically assisted fuzzing, which is the base of kind of the standard approach to cyber reasoning systems today, and this human-assisted cyber reasoning systems. And we found that, as expected, high semantic complexity is highly correlated with how much humans can help. Now, of course, there's a caveat here. In our data set, there's very few programs that are low semantic complexity. This This isn't very solid statistical evidence, but it seems to imply what we were thinking in the first place. But a surprising thing is that the expertise required wasn't such a big deal. We found that using the static analysis suggestions, people were able to actually create inputs, test cases that would properly exercise these programs, even when programs were programming language interpreters. So the static analysis really helped in this case. We achieved a much larger code coverage, so about an 8.5% improvement over Driller, and then of course an associated improvement in the number of crashes, of 20 crashes additional on top of the 36 that Driller found. This was an interesting thing because the increase in code coverage isn't such that I would expect to see that high increase in the amount of crashes. From looking at some of these test cases, even when humans didn't trigger a huge amount of extra coverage, they did drive the execution into interesting dynamic states of a program. And again, this is something that we really, as a community, lack a good language to talk about. And you'll notice that a side effect of this is that the HaCRS experiments tended to generate fewer test cases than the Driller and the fuzzer experiments. And this is because, again, these test cases were individually each more meaningful and would then get synchronized back into the automation to be mutated into other meaningful test cases. The relative improvement in terms of code coverage was 20%, and that led, or 19%, which led to a 55% improvement in the number of crashes found. That was pretty interesting. Another interesting thing is that we found that semi-experts did not do significantly better than non-experts. Again, there were very few semi-experts. But from talking to them afterwards, I think that the reason they did they did not do better is because we have an interface that is very highly targeted toward non-experts. So this kind of infers some next steps in the field of human-assisted cyber reasoning systems. Again, this is the very first steps toward it, this paper. There's still a lot to do here. For one thing, I just mentioned this utilization of expertise. We need better interfaces for more expert humans to assist these systems. Another one I'll briefly mention is incentive structures. I mentioned we paid out, we wanted humans to trigger N branches that had not been previously triggered in the program, and we gave this as a raw number, as in 10% of the previously untriggered control flow transitions. That is misguided. We don't actually care how many control flow transitions the humans trigger. We want them to aid cyber reasoning systems in the analysis of software. So a better incentive structure that measures the helpfulness of the human to the automation would be better. And then other applications of human assistance that we discuss in the paper that I don't have time to go into right now. So again, this work is in collaboration with my illustrious co-authors. The two bolded ones are on the market. Make sure to hire both of them. You can find this presentation online. The project materials on HaCRS.org. For some reason, the paper is not on the conference website, but it's on HaCRS.org. We've upstreamed all the improvements to Anger. You can use those right now, and we're working on getting the that human-facing web interface up on HaCRS.org as well. And if you're interested in this sort of stuff, join us on the Anger Slack. That's the invite link to our Slack. Shoot us a PM, and let's talk about projects. And I'll take any questions.
Okay, so we have some time for questions. Just come up to the microphone.
Hi, Ann from the University of Virginia. So during the Cyber Grand Challenge, you had the opportunity to snoop on network traffic. In some ways, the network traffic gives you traffic. Can you characterize the difference between capturing network traffic and having these Amazon Turks sort of people giving you more inputs?
So the interesting thing with that difference between network traffic and the humans is that, I'm not going to rewind all the way to it, but in that interface, we presented the other test cases that we've been able to recover to the human. And so it's a more interactive process. Network test cases, you get the network test case, and if they're usable, they're usable. If not, or if it triggers something new, it triggers something new. If not, you're out of luck. This is a more interactive process, so you can really push the human to provide inputs or test cases that trigger new functionality.
So qualitatively, it was better then to have the human in the loop. Is that what
Yeah,
you're saying?
So it's a little tough to measure because we didn't. Our network synchronization part of the cyber reasoning system crashed partway through the Cyber Grand Challenge, but our results on this data set is better than the automation with the synchronization. I don't have that experiment in the paper, but we have the data for that.
Hi, Abhikra Chaudhary from NUS. I just had a clarification. So is it fair to say that you have the human interface as providing test cases because your backend can only process these test cases and generate more tests in the neighborhood? Because one can think of the human provided some other kind of assistance, like try to reach this intermediate location.
Yes, and this is, I'm really glad you asked this. This is what I meant here by static detection triage.
Okay.
This is something that we're hoping to get to in future work. I think there's a lot of different interaction points that you could have humans plug into.
That's right. If the test generation tools could process that kind of input, then one could think of
Exactly. Brilliant.
Hi. So when you were talking about expertise, you seem to be talking about technical expertise. How do you think your results would differ if you were looking at expertise in the actual system? So that a lot of systems, you have people who use them all the time versus people who never use them. Would that be any different?
So you're saying the specific software that you're analyzing?
Yes.
I think it would. We didn't really have this in our research protocol, but we had a, so we couldn't really measure it directly, but from people reaching out to us from help, you could see people that had a QA background, for example, approached this problem a lot differently than people that did not. They weren't, we couldn't really measure if they were more effective. Anecdotally speaking, we had effective people that had no computing background whatsoever, and effective people that had a QA background. I think it's a very interesting thing to explore, and my hunch is that it would be a big change.
I'm David. Thanks for the talk. I was wondering, did you have any people who were like just completely random? They just picked whatever and didn't really take into consideration your gamification and stuff like that?
Oh yeah, we had. I mean, we had some complete chaos sort of situations. Look at some test cases, and it's people typing in obscenities and.
Okay, but did they also increase the
No, most of them did not trigger significant additional coverage and did not really help the system.
Right.
This 183 human assistants, there's a long tail of people that are not very effective in helping the system and people that are.
Okay, interesting. Thanks.
This was great. Plenty of good questions. So let's thank the speaker again.